Hello, Accelerated Chemistry students. This is Miss Christopher, and this is your Chapter 10, Section 3 video notes all over percent composition of a compound. So what is percent composition of a compound? The relative amounts of the elements in a compound are expressed as the percent composition or the percent by mass of each element in the compound. So if we look at this example, we have potassium chromate. And in the pie chart, you can see that all of the element percentages add up to 100, but each element is not in the same percent because it has to deal with how much mass is in the compound as a whole. Like I said before, all of the percents must add up to 100 because you're talking about one whole compound. Since the percents must add up to 100, you would assume that if the compound has the same elements in it, they would be the same. However, the ratio is very important. Notice we were talking about potassium chromate on the left and potassium dichromate on the right. There are more of each element in potassium dichromate, and so your percentages are going to change based on the mass of each element versus the mass of the whole. So with that being said, if you know the relative masses of each element in a compound, you can calculate the percent composition of the compound. And you can do that by using the mass of an element in the compound, dividing it by the whole mass of the compound, and then multiply it by 100. So here's your equation. The percent by mass of an element is equal to the mass of the element over the mass of the compound times 100. So how does that look in a problem? So let's look at an example where we have 13.6 grams of a compound that has magnesium and oxygen in it. And when it decomposes, we have 5.4 grams of oxygen. And we want to know what is the percent composition of this compound. So what is the percent for each element? So we're going to list what we know and unknow first. We know that in order to solve this problem, we need to know that the mass of each element and the mass of the compound, and we're going to take that ratio and multiply it by 100. So we know the mass of the compound, we know the mass of oxygen, and we can get the mass of magnesium by taking the mass of the compound minus the mass of oxygen. What we don't know is the percent by mass of each of the elements, magnesium and oxygen. So let's look at magnesium first. So when we solve for the percent by mass of magnesium, we're going to take the percent of magnesium is going to be equal to the mass of magnesium over the mass of the compound times 100. And for magnesium, we have 8.2 grams. Where did this number come from? Remember, we subtracted the mass of the compound minus the mass of the oxygen over the mass of the compound times 100. So 8.20 grams over 13.60 grams times 100. Grams cancel. Our answer is going to be 60.29% magnesium. I like all of your percentages to be rounded to 2 decimal places for the future. Now we can do the same thing for oxygen. So the percent of oxygen is equal to the mass of oxygen over the mass of the compound times 100. Remember, the mass of oxygen is 5.4 grams. Mass of the compound is 13.6 grams. We're going to multiply that by 100 because we want a percentage. Grams cancel again, and we end up with 39.71% oxygen. Now, how do we know if we did this right? The percentages should add up to 100, and they do. So we're good. Now, we can also calculate the percent composition of a compound using its chemical formula. So remember, the subscripts in the formula are used to calculate the mass of each element in a mole of that compound. So we can use the individual masses of the elements and the molar mass and can determine the percent by mass of each element. So that looks like this formula. So percent by mass of each element is the mass of the element in 1 mole over the molar mass of the compound times 100. So of course we're going to have a problem over that. So let's look at propane. Propane is C3H8. Let's calculate the percent composition of propane. So first, we're going to calculate the percent by mass of each element by dividing the mass of that element in 1 mole, or the molar mass, divided by the mass of the compound, and then multiply that by 100. So first, we know what mass we have of carbon in 1 mole of propane. Because we have 3 carbons, we're going to multiply the molar mass of carbon by 3. Because we have 8 hydrogens, we're going to multiply the molar mass of hydrogen by 8. We're going to add that up together, And we don't know the mass percent of carbon and the mass percent of hydrogen. So this is pretty easy. Basically, what you're going to do is you're going to take the mass of each element within the compound and divide it by the molar mass. So let's look at how that looks. So if we were to determine the percent by mass of carbon in C3H8, we would take the mass of carbon in 1 mole of C3H8 over the molar mass of propane. So we would take 36.03 divided by 44.09 times 100, and we get 81.72% carbon. We're going to do the same thing for hydrogen. So we would take the molar mass of 8 hydrogens, which is 8.064, divided by the molar mass of propane, which is 44.09. We're going to multiply that by 100, and we get 18.29. Once again, since we're dealing with percentages, how do we know that we did this correctly? Your percentages should add up to 100, and when they are expressed to two significant figures, they do. So now let's talk about using the percent composition as a conversion factor. So you can use percent composition to calculate the number of grams of any element in a specific mass of a compound. To do this, you're going to multiply the mass of the compound by a conversion factor based on the percent composition of the element in a compound. And another way to say this is that if you know the molar mass or the mass of the compound that you have, and you know what percentage of that mass is each element, take your mass of the compound, multiply it by your percentage, and that will give you your mass of each element in the compound. So we found out from the problem before that propane is 81.8% carbon and 18% hydrogen. So we can change these into conversion factors. So we know that in 100 grams of propane, 81.8%, 81.8 grams of that is carbon. And we know in 100 grams of propane that 18 grams of that is hydrogen. So we can set this up and solve for the mass of carbon and the mass of hydrogen in an 82-gram sample of propane. So what would that look like? So if we were to list how we were going to do this, we would go from grams of propane to grams of carbon and grams of propane, and then go to grams of hydrogen. So we know the mass of the propane sample we have. We don't know the mass of the carbon, and we don't know the mass of the hydrogen, but we do know from the problem before what the percentages of each are. So we're going to calculate the mass of carbon first. So here is our percent that we got. Remember, it was 81.72% of carbon in propane. So that's over 100 grams. So when we set up our conversion using that information, this is what he looks like. Grams of propane cancel. When we do our math, we get 67.1 grams of carbon. Now, when we do it again for hydrogen, we're going to do the same thing. Remember, where did we get that 18.29? That was from the percent calculation in the problem before. And we can use that as a conversion factor again. Grams of propane cancel, and we are at 14.9 grams of hydrogen. Pretty easy enough. Now, how do we check our math? They should add up to the original mass that we started off with, which is 82, and they do. When you add them together. Works. Now let's talk about empirical formulas. The empirical formula of a compound gives the lowest whole number ratio of atoms or moles of the elements in the compound. An empirical formula may or may not be the same as the molecular formula. So, the percent composition of a compound can be used to calculate the empirical formula of that compound. So, the percent composition is going to tell us the ratio of masses of the element in a compound. Then we're going to change those ratio masses into ratio of moles by using the molar mass of each element. Then we're going to reduce that mole ratio to the least whole number to obtain the empirical formula of the compound. In other words, memorize this. You're going to go from percent to mass, mass to mole, divide by small, and multiply until whole. What does that mean? Well, let's do an example problem. So we have a compound that contains 25.9% nitrogen and 74.1% oxygen. So what is the empirical formula? So let's go through that poem step by step. First step, percent to mass. So you're going to assume that you have a 100-gram sample and convert all of your percentages to masses. So if we have 25.9% nitrogen, that means that we have 25.9 grams of nitrogen if we have a 100-gram sample. That assumption has to happen every single time. Same thing for oxygen. We have 74.1% oxygen. That means that we're going to have 74.1 grams of oxygen. Next, convert your masses to moles. So convert the masses of each element into moles of each element by using the molar mass of the element. So for nitrogen, we're going to multiply that by molar mass. Grams of nitrogen cancel, and we're left with, notice how I didn't round this number. You need to write down every single solitary decimal place. Why? Because if you round too soon, you will get the wrong answer. Do the same thing for oxygen. Grams of oxygen cancel, and we get 4.63125 moles of oxygen. So we just determined how many moles of nitrogen are in this sample, how many moles of oxygen are in this sample. Now we need to figure out what the ratio of each is. So we're going to divide by the small. So determine which of the mole amounts is the smallest, then divide each mole amount by the smallest number of moles. So when we look at nitrogen, we have 1.848679546. And this is actually going to be the smallest one out of the nitrogen and the oxygen ratios that we just saw for. When I do that math, I get a 1. Oxygen, on the other hand, when I divide it by my nitrogen mole amount, I get 2.5. Notice how I still have not rounded my answer yet. Next, what we're going to do is we're going to multiply to a whole. So we're going to determine what factor you need to multiply each mole amount by to get a whole number. Well, nitrogen is a whole number, so we're okay. But oxygen's the problem, and it's 2.5. So what factor can I multiply 2.5 by to get a whole number? Well, the answer to that is 2. And since I'm multiplying oxygen's mole amount by 2, I need to multiply nitrogen's mole amount by 2. So that means I have 2 nitrogens and 5 oxygens. So now we've done all the math needed to solve this problem. Now we actually need to write the formula. So now we're going to write the formula. So place the whole number ratios as the subscripts for each element. So nitrogen, remember we solved it was a 2. Oxygen, remember we solved it was a 5. Pretty self-explanatory if you follow that poem. If you skip a step or if you round prematurely, you will get the wrong answer. So, does it make sense? Well, it does make sense, this answer N2O5, because the subscripts are whole numbers and the percent composition of this empirical formula equals the percentage given in the original problem. So now let's talk about molecular formulas. The molecular formula of a compound is either the same as its experimentally determined empirical formula, or it is a simple whole number multiple of its empirical formula. So once you determine the empirical formula of a compound, you can determine its molecular formula if you know the compound's molar mass. So you can calculate the empirical formula mass of a compound from its empirical formula. Then this is simply the molar mass of the empirical formula. Then you can divide the experimentally determined molar mass by the empirical formula mass. And the quotient is going to tell you what the multiplier is that you need to multiply your empirical formula by to get your molecular formula. That does not make any sense, so let's do a problem. So we're going to calculate the molecular formula of a compound whose molar mass is 60.0 grams per mole, and the empirical formula is CH4N. So let's start off. What do we know? We know the empirical formula, we know the molar mass, but we don't know what the molecular formula is. So first things first, we're going to calculate the empirical formula mass. When we do that, we get 30.052 grams per mole. Next, what we're going to do is we're going to divide the molar mass by the empirical formula mass. So the molar mass given in the problem was 60. The empirical formula mass was about 30. And when we divide that out, we get 2. So then we're going to take our empirical formula, which was CH4N, and multiply that by 2 and get C2H8N2. And how do we know that we did this right? Well, if you determine what the molar mass is, you would get about 60, and that's how you know it is correct. Well, that was a lot of information in chapter 10, section 3. So tomorrow we're going to look at all of that information in class. As is always, all the information on these Google Slides has been acquired and adapted from Pearson Chemistry's 2012 edition textbook resources CD and pearsonchem.com. Thank you so much. Have a good night.